I'm going to present an introduction to recurrent neural networks, or RNNs. We'll be exploring how RNNs help computers understand sequential data, like text, speech, and time series information. By the end of this talk, you'll understand how RNNs work, why they're necessary, and what challenges we face when using them. Let's get started. Let's start with the fundamental problem. Traditional neural networks, like MLPs and CNNs, were designed with some key assumptions. They expect fixed-size inputs, treat all features as independent, and don't care about the order of inputs. But when we work with sequential data, think of sentences in text, audio waves, or stock prices over time, these assumptions break down. The length of sequences varies. The meaning of each element depends heavily on what came before it. Order is absolutely critical, and the model needs to remember earlier steps to make sense of later ones. Standard neural networks simply don't have a built-in way to remember past information. They process each input independently, so they can't capture these temporal dependencies. For example, if you're trying to predict the next word in a sentence, knowing the previous word completely changes what word makes sense next. That's where RNNs come in. RNNs are neural networks specifically designed for sequential data. The key difference from feed-forward networks is that RNNs feed information back at each time step. They maintain what we call an internal memory, or hidden state, which captures context from previous inputs. Let me give you a practical example. Imagine predicting the next word in a sentence. An RNN processes each word one at a time, but it remembers information about all the previous words. This memory allows it to predict not, is more likely to follow it is than something else. That's the power of recurrence. Now let's see how RNNs differ from standard feed-forward networks. First, memory. Feed-forward networks have no memory, while RNNs maintain a hidden state across time steps. Second, the type of data they handle. Feed-forward networks work with independent inputs, while RNNs are built for sequential data. Third, their typical use cases. Feed-forward networks excel at image classification, but RNNs are ideal for text, speech, and time series. Finally, weight sharing. In feed-forward networks, each layer has different weights, but in RNNs, the same weights are reused across all time steps. This weight sharing is crucial because it allows RNNs to handle variable length sequences efficiently. Let's dive into how RNNs actually work. The core idea is something called a hidden state, which I'll call H_T. This hidden state carries memory through the network. At each time step, several things happen. We take the current input X_T, we take the previous hidden state H_T1, and we compute a new hidden state H_T and an output Y_T. The crucial insight is that the same cell and weights are reused for every time step. This reuse is what allows RNNs to handle variable length sequences. Whether you have 5 words or 500 words, the network structure stays the same. The first key component is the recurrent neuron. This is a neuron that maintains a hidden state and passes information from previous time steps forward. It captures dependencies across time by receiving both the current input X_T and the previous hidden state H_T1, then produces a new hidden state H_T. In a way, the hidden state is the network's memory. It remembers relevant information from everything that came before. The second key component is something called RNN unfolding or unrolling. This is a conceptual tool that helps us understand and train RNNs. Imagine unrolling the recurrent structure over time steps, T_1, T_2, T_3, and so on. Each time step becomes like a separate layer in a traditional deep network. The sequence is expanded horizontally through time, with shared weights across all steps. This unfolded view is essential for training via something called backpropagation through time, which we'll discuss shortly. It allows us to see how information and errors flow through the entire sequence. Let's talk more deeply about the hidden state. At each time step, the RNN computes H_T, a vector that stores information from all previous steps. Each input X_T influences both the current output and the next hidden state, creating a chain of memory through time. We can visualize this as a state matrix S that holds all hidden states from time 1 to time n. This matrix is essentially the complete memory of the sequence. Now for the mathematical heart of the RNN. Here's the equation for computing the hidden state. H_T equals the activation function applied to the sum of 3 terms, U times X_T, W times H_T1, and a bias B. Let me break this down. U is the input weight matrix. It transforms the current input. W is the recurrent weight matrix. It transforms the previous hidden state. Adding these together creates a combination of current and past information. The activation function, usually ton or real U, squashes this to keep values in a reasonable range. There's also an alternative notation using W_HH for recurrent weights and W_XH for input weights. Both formulations mean the same thing, just different notation. The key is, current hidden state depends on both new input and past memory. Once we have the hidden state, computing the output is straightforward. At each time step t, we calculate y_t equals the activation function O applied to v times h_t plus a bias c. Here, v is the hidden-to-output weight matrix that transforms the hidden state into our final output. The activation function O depends on your task. For classification, you'd use softmax. For other tasks, sigmoid or ReLU might be appropriate. So the output is just a learned transformation of the hidden state. Let me walk you through what happens at every single time step. First, we take a new input x_t. Then we combine it with the previous hidden state h_t1. From this combination, we compute an updated memory h_t. We produce an output y_t. And we pass h_t forward to the next time step, where it becomes h_t1 for that step. This loop, repeated over the entire sequence, is what creates temporal understanding. Each step processes its input using a fixed activation function, usually TON or ReLU, which helps the network learn smoothly. The hidden state acts as the network's memory of prior steps, allowing it to capture short-term and even some long-term dependencies. This is the fundamental mechanism that makes RNNs work. Now, how do RNNs actually learn? Regular backpropagation doesn't work well for RNNs because it only handles layer-by-layer computation. RNNs have temporal dependencies, so we need something special. Backpropagation through time, or BPTT. The key insight is that outputs depend on previous hidden states, which came from even earlier inputs. To properly learn these dependencies, we need to propagate errors backward through time. BPTT allows the network to learn from past sequence context by calculating how each weight affects the entire sequence, not just one time step. Here's how BPTT works in principle. First, we unroll the RNN over all time steps. Remember the unfolding concept? This turns the recurrent structure into something that looks like a deep feed-forward network. Then we compute hidden states for each step going forward through the sequence. We calculate the output and loss at every time step. Finally, we backpropagate errors from the last time step all the way back to the first, updating weights as we go. This backward pass is crucial because it accounts for how early inputs affect outputs far down the sequence. RNNs are flexible and can handle different input/output configurations. First, one-to-one, single input to single output. This is just a standard neural network with no sequential dependency, basically not using the RNN's recurrent properties. Example, binary classification. Second, one-to-many, single input to a sequence of outputs. This is useful when one input should trigger multiple outputs. The classic example is image captioning. One image produces multiple words describing it. Continuing with the other configurations. Third, many-to-one, a sequence of inputs mapped to a single output. This is useful when you need context across an entire sequence to make a decision. The example here is sentiment analysis. You read through a whole sentence and decide if it's positive or negative. Fourth, many-to-many, sequence to sequence. This is for tasks requiring sequential outputs, like machine translation, where a sequence of words in English becomes a sequence of words in French. Each configuration serves different real-world problems. Now let's discuss the limitations of vanilla RNNs. There are three main problems. First, vanishing gradients. When we backpropagate through many time steps, gradients become exponentially smaller. This means the network forgets long-term dependencies. Second, exploding gradients. Conversely, gradients can grow too large, causing unstable training and making the network diverge. Third, vanilla RNNs struggle to capture long-term dependencies because of these gradient issues. However, there are some training tricks that help. Use TON or ReLU activations carefully. Use gradient clipping to prevent exploding gradients, literally capping the gradient size. Initialize weights with small random values. And remember, vanilla RNNs work best for short sequences, or when long-term memory isn't crucial. For longer sequences, we need architectures like LSTM or GRU.